Welcome everyone. In this video we are going to analyze a conical pendulum and then we're going to derive a formula for the period of that conical pendulum. So the question is, what is the period? Period question mark. Now the first thing to do is actually draw a diagram of a conical pendulum. So there is going to be let's say a glass tube. Okay, this isn't that important, but let's say it's a glass tube. And through this tube, there is going to be a rope. Okay? There's a rope. And on the lower end, there is a mass attached. Let's call that mass 1, M1. And if there is mass 1, you can kind of guess that there's going to be a mass 2. And there, in fact, is a mass 2. Mass 2 is connected to the other end of the rope. We have mass 2. Okay? Now, the thing is, we're going to hold this apparatus, hold this setup from the glass tube, and we're going to start swinging it. Okay, we are going to rotate it so that M2 will go around the circle. And when we start rotating it, we want to make sure that M1 doesn't go up or down. We want to make sure that M1 stays at rest. So when we are applying a force, when we are rotating the system, not the system actually, we're just, well, you can probably imagine what I'm talking about. We're just exerting some force so that M2 rotates and M1 is constant. It stays at its place. It is at rest, okay? So we have M1, it did not change its height. And there is M2. So maybe, well, hold on, okay. So we have M2, let's say, and that's not how it's going to be. So I'm trying to make it a bit realistic. Sorry about my poor drawing ability, okay. So it's going to be something like this, let's say. Here we have M2, and it is going to be traveling around the circle, like this. Now the thing here is, you can also see why this is called a conical pendulum. Look at this shape that M2 makes while it is traveling around. It is going to kind of form a cone, right? That's where the name comes from. But you might say, why would M2 go down when we start rotating it? Sure, if we were to do this in real life, you would see that in fact happens. But why does it need to do that? Maybe if one of the masses is heavier than the other, that wouldn't happen. Who knows? Well, in fact, by the end of this video, you will know whether or not this would happen all the time. There is in fact a condition between M1 and M2. And that condition is, you can pretty much guess what the condition is going to be. One of them needs to be greater than the other. And we're going to see which one needs to be greater. Okay? But this is the setup. We want to find the period of the motion of M2 as it goes around the circle. And this circular path is on a plane. It is on a horizontal plane. That is, M2 is not moving up or down. This is going to be important for our derivation. Cool. So the best way to start this is by drawing two free body diagrams. First for mass 1. So free body, and let me change colors. Sorry about that. Free body diagram 1 and free body diagram 2. Free body diagram 2. Now for the first one, there is M1G downwards, right? And then there's going to be the tension force upwards, which I will call Ft. This is the force by the rope, and we're not caring about any frictional forces. We are neglecting all frictional forces. So this is all the forces. These two are all the forces that act on the first object. Now for the second one, there is M2G downward. And there is the tension by the rope. It is going to be along the rope, and it is a pulling force. So it is something like this. And it is the same force. It has the same magnitude here and here, because we are also assuming that we are dealing with a massless rope. Okay? Now, I want to define an angle, and the angle is going to be here. This is angle theta. That is the angle that the rope makes with the horizontal. Okay? If we were to look at this setup from the side, this is... And we can imagine the road as it is a very tiny road. And in fact, it is most of the time. So this is the direction, this is the road, let's say. And then we're going to have the angle here. This is theta, okay? And you can assume that this is like a triangle. And yeah, this is theta, and if that is theta, this angle is also theta, so this part is also theta, okay? This is theta. Cool? Now, one more thing to note is if, let me draw that again. So if this is theta, right? And the mass 2, this is mass 2, it is going around a circle like this. So maybe it's like, it continues on like that. And the radius will be, and if we're thinking, well, let's say that mass 2, when we drew it like this, it is at the furthest out right point, okay? This is as right as it gets. So it is like here, when we drew that. Let me erase this dashed line. Okay, this is at the rightmost point. If this is the rightmost point, then this is the radius. And this is the length of the rope. So what is the radius of the circular motion? It is L sine of theta, right? Because R is the opposite side if you're focusing on theta. And we're going to need this. That's why I wrote this. Maybe we won't. I don't know. Yeah, we might need it. Why not write it then? Okay, so. Alright, now we can write the force equations. Using the first diagram, we are going to say that force of tension equals M1G. And we are able to say this because we are making sure that while doing this experiment, we keep an eye on M1 to make sure it doesn't move up or down. We want it to be at rest. Okay? This is very hard to accomplish while doing it yourself, and that is a flaw in the experiment, right? Maybe if you were doing this, you could list that as a source of error. You could say that we were trying to keep mass 1 at rest, but that was very hard to do. And for the using the second diagram, as we discussed, the circular motion takes place on a plane, on a horizontal plane. So the mass 2 is not moving up or down, which means that the net force in the vertical direction on M2 is 0. So Ft cosine of theta equals M2G. And at this point, we can make the constraint that we were talking about. Now, cosine is going to be at most 1, right? It is at most 1. And for that, the theta would need to be 0. So it is not very applicable. I mean, if there is a theta in the setup, if there is a conical pendulum, theta can't be 0. So cosine here can't be 1. It is something less than 1. And if this is something less than 1, this means that this is less than Ft, right? We multiplied Ft with a number that is less than 1. So the result is something that is less than the tension. And Ft is M1G. So M2G is less than M1G. So G is simplify. Oops, sorry about that. G is simplify. And we get that M1 is greater than M2. This is the restriction that I was talking about. You need a heavier mass as the M1. Okay. Now, if we write another force equation using the second diagram, if we are focusing on the centripetal motion going on, the circular motion going on, and we are making sure that this is a uniform circular motion, we can say then the direction of the centripetal acceleration is in this direction. It is towards left on the diagram that I drew, and there is only one force that is in that direction, that is Ft sine of theta. This needs to be equal to, well, it's going to be mass 2 times the centripetal acceleration, which is omega squared times r, the radius. And omega is the angular velocity of the motion. And what is r? It is right here. If we can substitute that, L sine of theta. Sine of theta simplifies. And for Ft, we can substitute M1G. Let's do that. M1G equals M2 omega squared L. Now, we know that omega is equal to 2 pi over t, since this is a uniform circular motion. And t here is the not the tension, excuse me. T is the period, okay? It is this period that we're looking for. Maybe I can even mention that it is the period. Okay, so we said this because this is a uniform circular motion. when mass 2 goes around the circle once, it covers 2 pi radians, and it takes a t amount of time to do that. So the angular velocity is 2 pi over t. So we make that substitution, m2 4 pi squared over t squared L, which means that t squared is equal to, let's see what it is equal to. It is going to be 4 pi squared m2L divided by m1G. Okay? And let's make sure I got it right. Yes, it looks quite right. And if you want to find the period, just take the square root of this, and let's just do that here. So the period is 2 pi. We have the square root. It's going to be m2L over m1G. And this is the formula. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. So for that, please make sure to subscribe, and that's it. Until then, take care.